Okay, good morning, everybody. Let's get started. Okay. So what we're going to be doing today is we're going to do two things. We're going to look at what happens when we have more than two poles or extra zero. And after we finish that, we're going to start the next topic, which is the steady state errors. Okay. So in the previous classes, we looked at the second order system, and we understood the classification of the response of the system: underdamped, overdamped, critically damped. We're familiar with knowing, based on the location of the poles of the system, we are able to determine all the characteristics of the response of the system. Everybody familiar? If we have poles, if it is underdamped, then this distance is zeta omega n. This is omega n 1 minus zeta squared. This is omega n. And from these, we can determine all the parameters. And this is this theta, the cosine of this theta is zeta. So therefore, if we know the poles of the location of the second order system, we should be able to calculate all the characteristics of the response. Now, what happens if we have a system where we have a third pole in the system? So let's look at a system that is a third order. And therefore, the transfer function, g of s, is given by something like this: omega n squared, s plus alpha, multiplied by s squared, plus 2 zeta omega n, multiplied by s, plus omega n squared. Now, if we did not have the s plus alpha, this is a typical second order system. But now we have an additional pole to this system. And we're going to see how we can determine the response of the system, and when is it we can use the information that we have about the second order system to study the response of this system. So what is our inclined to do? Our inclined is to try to approximate this with a second order system, because then we can use all the development that we've done for second order system. So let's see in what conditions we can approximate this system with a second order system. So if we have this third order system, and I want to calculate the step response for this system, it's going to equal to the input multiplied by the transfer function, and then we can do partial fraction expansion. We can write this as 1 over s plus b over s plus alpha. And we expand the third part as b multiplied by s plus zeta omega n. Let's call this b1, plus c multiplied by omega d divided by s plus zeta omega n squared plus omega d squared. So this is the partial fraction expansion of this expression, of this response. Okay, so then we can calculate the inverse Laplace of the step response. We're going to get a multiplied by u of t plus b1 e to negative alpha multiplied by t plus e to negative zeta omega n multiplied by t multiplied by b cosine omega d multiplied by t plus c sine omega d multiplied by t. So again, this is a third order system, and therefore it has a second order in it and additional pole. The s plus alpha is the added pole. So to see how the response of this system would look like, you're going to run some MATLAB and see what happens if we have the poles of the second order system and we have a real part that is at 1. So we're going to just normalize this so that the second order system poles are at 1. And we're going to add the extra pole that we have at negative alpha. Does that make sense? So we have a second order system. These are the poles of the second order system. And alpha is the third pole that we added. When alpha is equal to 1, this means it's aligned with the poles here. And when alpha increases, it means it's going farther away from the poles of the second order system. Okay. So with that, we'll run our MATLAB. So what MATLAB is going to do is going to plot the response for various values of alpha. So looking at the response here. So if you look at the graph here, this represents, let me capture it. Where is it? Okay. So we'll explain on this and then we can show the actual graph. But if you look at this graph here, what does this represent? The starred response. A second order system. The yellow is the second order system. Is that clear? Make sense, everybody? And then we're adding a third pole, and the location of the pole goes from 1 all the way to a 10. Is that clear? So the second order system, the poles, the real part is at 1. And then we have another pole, a third pole, that changes from 1 all the way to a 10. So if you look at the extreme most, when the third pole is located at alpha equal to a 1, so this is the case when it is circle, what is the response that we're getting? The one that is here. So this is alpha equal to a 1. Does that make sense? And then all the way to alpha equal to a 10, alpha equal to a 10 is the response that we get here. Does that make sense, everybody? So this is a second order response. And then we have a third pole that varies from 1 all the way to 10. So if you look at this graph, what can you conclude from the location of alpha and the response of the second order system?
The higher alpha is, the closer it is to
The farther alpha is from the second order poles, the more likely I can approximate the third order system with a second order system. Does that make sense? So when alpha here is 10, the response looks almost as if it is of a second order system. This is the response of the third order system. It's very close to that of the second order system. This is when alpha is 9, when alpha is 8, when alpha is 7, when alpha is 6. However, when alpha is very close to the second order system, which is the case when alpha is equal to a 1, we see that the responses are very different. You see it? When alpha is equal to a 1, which means I have alpha equal to a 1, means I have the poles of the second order system somewhere here, and I have the third pole that's also on the real axis at the same location. So in that case, we see that the difference between the second order and the third order is substantial, that we cannot approximate the third order with a second order system. However, if I look at the response here, when alpha is 10, I have the second order system, which is at 1, and alpha is all the way here at 10. And in this case, I can approximate the third order system with that of a second order system. Everybody convinced? Make sense? Okay. So therefore, we can make some observations. And the first observation, when the extra pole is within a factor of 4, and that means compared to the location of the second order system, it will have considerable impact on the response. However, when alpha is greater than 5, then we can approximate the third order system with a second order system. Okay. Now also, if you look at all the graphs, what is the impact of the third order system? What the impact, the one parameter of the response that is affected the most by the third order pole? The rise time. If you look at the rise time, what happens when we added a third pole? The rise time got larger. So a third observation, the rise time the extra pole increases the rise time. Sounds good, everybody? And remember, why is it when we have an extra pole and the pole is at alpha that is at 10 compared to this location, we can approximate it? How is that consistent with what we discussed previously? What happens when the pole is very far from the j omega axis? It's very fast. Make sense? So we have all these poles. These poles are very slow. This pole is very fast. And therefore, it is fast enough that the slowest poles will determine the response of the system. Does that make sense, everybody? So that's consistent. If the pole is very far away, then we can assume it is so fast that it really have minimum impact on the response of the system. Okay. The next thing we're going to see is what is the effect of additional 0 on the response. So let's have a typical transfer function, g of s, that is equal s plus a divided by s plus b multiplied by s plus c. And therefore, we can write it as s plus c plus a divided by s plus b multiplied by s plus c. So how is this different than the second order system? A typical second order system. We have the s here. In the second order system, this was a constant, the numerator. Here, we have s plus a, which means we have an extra 0 in the transfer function. Okay. So if we came to a second order system and we applied a unit step, and we got a response c of s that is equal to 1 over s multiplied by s plus b multiplied by s plus c. And this will give us c of t. What is this? A second order system. We applied a unit step. We got the response 1 over s. We can do partial fraction expansion and get the response, a typical response of a second order system. Now what happens if we came to g of s and we applied the same input, r of t equal to u of t? What is the response going to equal to? Excellent. Y of s is going to equal to a multiplied by c of s plus s multiplied by c of s. That's what you meant to say? Is that clear? Make sense? If I take only the denominator and the numerator is 1 of this, and I call this the response of that part, C of S, then if it is multiplied by S plus A, the output is gonna be A multiplied by C of S plus S multiplied by C of S. Everybody sees that? Okay. Now what does this represent if I look at this Y of S compared to the second order system? A is just a constant, so it scales this output of a second order system. And what is S multiplied by C of S? For people who recently took the exam.
Step response.
S multiplied by any C of S, what is it? Properties of Laplace transform? The derivative of the response, excellent. So this S multiplied by C of S represent the derivative of C of t. Does that make sense, everybody? So when we have a zero in the numerator, we're getting the response of the system plus the derivative of that response. Okay. So we're going to do something similar. We're going to run MATLAB with different locations of the zeros, and we're going to see when is it we can approximate the response with a second order system. So if I look at this response is when this is of the second order system. And then for different values of alpha, when alpha is 10, this is the response of the system. And all the way when alpha is 1, this is alpha equal to a 1. What do we notice? When alpha is large, what does the response of the system look like? It looks like we can approximate it with that of a second order system. Make sense? So looking at this graph, if alpha or A, or we called it A, sorry, A equal to 1, A equal to 10. When A is large, we can approximate the response as following. Y of S is going to approximately equal to A multiplied by C of S, and therefore Y of t is going to approximately equal A multiplied by C of t. Does that make sense? And you can see that also from here. What happens when A is very large? This term is going to dominate. And therefore, this term is going to become smaller. And therefore, we can approximate Y of S as A multiplied by C of S. Okay. So what happens if we have more than one extra pole or one extra zero? We might not be able to use the derivation that we've done with the second order system. Does that make sense? Now the second order system is very popular, and probably any time you see anybody analyzing a system, the first thing you're going to try to do is to approximate it with a second order system. Why? Because there is all these tools, and people are very familiar with second order system. So if you have the system If you have a system and you can approximate it with a second order system, great. Then you can use all these tools. You can say, I'm going to approximate it and use all these tools. If you can't, you can't. You just have to do whatever that response is going to be. Does that make sense? So we've done the second order system, and we tried to stretch it to see like what else can we include with the second order system. And the conclusion, if we have a third pole, and the third pole is much farther than the location of the second order system, we can still approximate it as the second order system. And we have a zero also that is farther, much farther than the location of the poles. We can also approximate it with a second order system. Any questions? Comments? All good? The next topic, now that we are familiar with the calculation of the response of the system, and now that we can model any system, is start to look at the performance of the system. And therefore, the next topic that we're going to be looking at is the steady state error of the system. Or I should write this as like this. Can you spell error wrong? Okay. So what we're going to do is we're going to look at the steady state error, and we're going to see what setup of the system or what parameters of the system will determine that steady state error. What is the steady state error? What is the steady state error? Yes, the difference between the input and the output as time goes to infinity. And that's the steady state. The steady state refers to time goes to infinity. And the error, we define it as the difference between the input and the output. Now, the test signals that we're going to be considering the steady state error for are the following. So the first is the unit step. Second is the ramp input. And third, parabola. So apparently, the steady state error is going to depend on the input we apply. And these are the three inputs that we're going to study and determine the error for. Is that clear, what we're trying to do? So we're going to look at different system configurations and be able to determine the steady state error for any of these inputs. A unit step, a ramp, and parabola. Okay. Now if you look at any system, what are the sources of error in the system? Any control system, any system that you apply an input to. That was a question. You understand mean error. Go ahead, sorry.
Okay, I said just about anything that affects the system, like externally or internally.
Like,
It depends on the system.
it was, which one?
It depends on the system, like what comes to.
Give me like just a source of an error in a system.
Like components.
Components, excellent. Components like failure or inaccuracy.
Right, right.
Inaccuracies. What other sources of error could happen? External noise. Okay. External or internal noise. / interference. What other sources of error that we can have in a system? Like if you were to build any system, any circuit, and blame anybody for the circuit not working, what are all the, you can, I mean, apparently, like, you're not going to find anybody to blame.
User error.
What is it?
Human error.
Human error.
Yeah, not the engineers.
Okay. So let's just add one more, and non-linearity. So we can have components we can approximate as linear, and then when we put them in, they might saturate, and therefore they might generate errors, etc. So there might be other sources of errors as well. Now, what we are interested in is not the steady state error that will result in because of any of these, but rather we are interested in the steady state error that is a result of the system configuration. Is that clear? So what we are interested in, what we're going to be analyzing, is the steady state error that results from the system configuration. Steady state error and we'll see what this means as we go. We'll see what we mean by system configuration. Okay. So what we're going to be doing in today's class, we're going to be populating a table. And this table is going to look like this. We're going to have an input, which is the unit step, the ramp, the parabola. So these are the inputs. And then we're going to look at different configurations of the system. We're going to call it type. And we're going to have type 0, type 1, type 2. And what we're going to be doing, we're going to be filling all these entries. Is that clear? Because you're going to feel lost in a minute once we start populating them. So I want this to be clear. This is the map of what we're trying to achieve. We're going to be looking at different inputs. We're going to define what we mean by system type. And then we're going to calculate or derive the formula for each one of these inputs and for each one of these types. Together? And again, we are interested in the steady state error that is result of the system type, the system configuration, not the sources that result from outside the system configuration. Okay. Now in doing all this, we're going to make an implicit assumption or assumptions. And the first assumption is that our system is stable. If the system is unstable, then there is no sense talking about a steady state error. And the second assumption we're going to make also in all this derivation is that we're going to assume we have a unity feedback. And we'll see at the end, if we don't have a unity feedback, how we can calculate the steady state error. Is that clear? Now, usually we have problem on the second exam. That will be a steady state error. And one time the system was unstable, but nobody checked for stability. So after that, when I give a problem, I say assume the system is stable. Okay. So let's look at a typical system with a unity feedback. G of S, R of S, positive, negative, C of S. What is this signal here? It's going to equal the input R minus C. And we call it the error signal. Now it just so happens that this error signal is the error of the system because it's the difference between the input and the output. Okay, so the setup that we're going to be deriving the steady state error for looks something like this. Unity feedback. We have G of S. If we have multiple blocks here, what is it we're going to do?
Diagram reduction.
We're gonna do reduction. This G of S is the equivalent of all the blocks that we have. This is the equivalent of all the system, unity feedback. And we're gonna assume G of S has a numerator, a rational function, N of S over D of S. We're going to take this numerator and the denominator, and we're going to write it as N1 of S multiplied by S to the N multiplied by Q1 of S, where neither N1 nor Q1 has a 0 at S equal to 0. That's the same as saying N1 of 0 is not equal to a 0, and Q1 of 0 is not equal to a 0. What does that mean? I have G of S, polynomial over polynomial. I'm going to take from the numerator and from the denominator any term that is S. I'm going to take it as a common factor. If there is anything in the numerator, I'm going to cancel it with the denominator. I'm going to end up with S to the power of N. Did anybody understand anything? No. So let's see what this means. So let's say we have G of S that is equal to S minus 1 divided by S multiplied by S plus 1. There is no S term in the numerator that I can take as a factor, so therefore it's going to stay as S minus 1. And S in the denominator is already out, so it's going to, I can write it as s to the 1 multiplied by s minus 1. There's no simplification that I can do. So in this case, what is n going to equal to? The n that is here, 1. Together? Okay. Let's do another example. G of s equal s squared minus s divided by s squared plus s. What are we going to do? We're going to take the s in the numerator as a common factor. So we're going to have s multiplied by s minus 1 divided, we're going to do the same thing in the denominator, s plus 1. These going to cancel. We're going to get s minus 1 divided by s plus 1. What do you not like?
Is n 0 or is it 1?
Here? What is n going to be? 1 or 0? 0. This, we can write it as s minus 1 divided by s to the 0 multiplied by s plus 1. And therefore, n is equal to a 0. Very good. Let's do another one. G of s equal s squared minus s divided by s cubed plus s squared. Same thing. We're going to take s in the numerator, s minus 1, divided by s squared this time, multiplied by s plus 1. What is this going to equal to? S minus 1 divided by s, multiplied by s plus 1. And therefore, what is n going to equal to here? 1. And we'll see in a second the significance of this n. Okay, let's do one more. S to the 5 minus s divided by s to the 4 plus s cubed. What is n going to equal here?
3.
2. Is that clear what we've done? We're taking any s in the numerator, we took it out. Any s in the denominator, we took it out. We simplified them. And then whatever left with s in the denominator, the power of it, we define it as n. Okay. Any questions? Clear? Okay. So this n, we're going to define it as the system type. So remember in the table here, we said we're going to look at different configurations. And we're going to be using the type as entry as the column of that will define the different entries. This n that we defined here is, we're going to call it system type. And therefore, as you can probably guess, it will play a major role in determining the steady state error of the system. Okay, let me ask you, what do you think this n is? Which one? 1 plus 2, 3, correct?
Yeah, I can count.
What is the significance of n in a system?
Is it the number of functions or of G?
I mean, you are in the right path.
Is it the number of power
Okay, good. Keep going.
Is it like the number of curves in the response?
I mean, use for Laplace properties and what you're saying. Put them together. What do you get? What is a 1 over s from Laplace properties? And s in the numerator, what was s in the numerator? A derivative, wasn't it? S multiplied by any function is the derivative. 1 over s, what is 1 over s? Integrator. 1 over s is integrator. So when n is equal to 1, it means this system has an integrator inside of it. When n is equal to 2, what does this system have? 2 integrators inside of it, and so on. Is that clear? So 1 over s represents an integrator. 1 over s squared represents 2 integrators. One over s cubed, or 1 over s to the n, represent n free integrators. Okay. Now, as we will see, this n, the system type, the number of integrators, is what's going to determine the steady state error, which is something we can almost imagine. Because if I'm looking at the steady state error, and I have an error signal here, and then this system is going to try to integrate it, what's going to happen when it integrates it? It's going to get bigger and bigger and bigger. Most likely, it's going to force that error to get smaller. Does that make sense? So it makes sense that the integrator is going to play a major role in determining the steady state error. If there is an error signal here, this error signal is very tiny, but then I have an integrator inside g of s, then this signal is going to start growing up, is going to drive the system to reduce that steady state error. Make sense, everybody? Okay, so let's mathematically now see how this system type will determine the steady state error for different inputs of the system. So our error signal, E of s equal R of s minus C of s, E of t equal R of t minus C of t, and the steady state error E steady state gonna equal the limit as t goes to infinity of E of t, which is gonna equal the limit as s goes to 0 of s multiplied by E of s. Where is this coming from? Final value theorem. Very good. Okay. Okay, E of s equal to R of s minus C of s. Therefore, it's equal to R of s minus G of s divided by 1 plus G of s multiplied by R of s. Which is equal to R of s multiplied by 1 minus G of s divided by 1 plus G of s multiplied by nothing. R of s multiplied by 1 minus G of s over 1 plus G of s. Okay. And we can write this as E of s equal R of s multiplied by 1 plus G of s over 1 plus G of s minus G of s. which is going to equal to R of S multiplied by 1 over 1 plus G of S. Therefore, the error signal E of S over R of S is equal to 1 over 1 plus G of S. Okay. So therefore, if I want to calculate the steady state error using the final value theorem, this is going to equal the limit as S goes to 0 of S, this is coming from the theorem, multiplied by R of S, multiplied by 1 over 1 plus G of S. And this is the expression that we're going to be using, or the formula we're going to be using, to derive the steady state errors for all the different cases. So this comes directly from this, using the final value theorem. So what does the steady state error depend on? According to this, the input and G of S. This is what will determine the steady state error. Okay. So what we're going to be doing next is we're going to be looking at different inputs and then different system types and calculating the steady state error. So starting with the first input, which is a step input. So if we have a step input, R of S is going to equal to 1 over S, and therefore the steady state error is going to equal the limit as S goes to 0 of S multiplied by 1 over S multiplied by 1 over 1 plus G of S, which is going to equal to S with S is going to cancel. And since I have a constant in the numerator, I can just write this as 1 over 1 plus limit as S goes to 0 of G of S. Together? So again, plug in here, S, R of S, 1 over S, S cancels with 1 over S. We have 1 over 1 plus G of S. When the limit goes to 0, it's the same as 1 over 1 when the limit of G of S goes to 0. Okay. So this is the steady state error when we have a step input. So let's see what that will translate to based on the system type. So we're going to calculate it when the system type is type 0. And therefore n is equal to a 0. And the second or next we're going to do when it is type 1 or higher. Okay. So if the system is type 0, then the limit as S goes to 0 of G of S is going to equal to G of 0. Agree? And therefore, this is just going to equal to a constant. We're going to call it Kp. And we're going to define this Kp as position constant. And therefore, the steady state error is just going to equal to 1 over 1 plus Kp. Agreement? Okay. So as an example, if I have g of s equal a over tau multiplied by s plus 1, what is the system type here?
N equals 1.
Is it 1?
Nope, it's 0.
0. Does everybody know why it is equal to 0? The system type here? Who thinks it should be 1? Who does not know what the question means? This is a type 0 system. Because if I take all the free s in the numerator, there's no free s in the numerator. If I take all the free s in the denominator, there's no free s. There's no s that multiplies this term. I cannot take s as a common factor. There is s here, but that's not the s we're talking about. S that multiplies the whole terms that I can take as a common factor. There is no s that I can take as a therefore s to the 0. So this is a type 0 system. And therefore, I can apply, since it's type 0, the steady state error is equal to 1 over Kp. Kp equals the limit as s goes to 0 of g of s. So Kp is going to equal the limit as s goes to 0 of g of s, which is going to equal to a. And therefore, what is the steady state error going to equal to? 1 over 1 plus a. Together? Now we're going to do all this derivation, so when we solve a problem, we don't have to go through all this derivation. We're going to using the summary table that we're going to generate by deriving for each input and different type what the formula for the steady state error. Does that make sense? So the same with the homework or the exam. I mean, on the exam, we'll have a problem like this. The expectation you're going to spend a certain amount of time, assuming you're going to be able to use the table. If you're going to start deriving it from scratch, it's going to take you the whole exam. Okay, reminder. Okay, so let's see what happens if we have a system that is type 1 or higher. So we have n that is greater than or equal to 1. Therefore, I can write g of s as equal to a numerator, p of s, divided by s to the n, multiplied by q of s. And n greater than or equal to 1. Now the steady state error, we see is going to equal to 1 over 1 plus the limit as s goes to 0 of g of s. What is the limit as s goes to 0 of g of s? What is it? Remember, p at 0 is not equal to a 0. Q at 0 is not equal to 0. Why is it p at 0 is not equal to 0? It cannot be 0. P at 0 cannot be 0. Q cannot be 0. Why? Because we took s as a factor out. Does that make sense? Everybody? Why is P and Q cannot equal to 0 when S equal to 0?
Because there's a constant there.
Because we took all the S from the numerator and the denominator and we took them as a common factor outside. So what we left is with a P that is not equal to 0 when S equal to 0 and Q that is not equal to 0 when S is equal to 0. N1 of 0 is not equal to 0. Q1 of 0 is not equal to 0. Because if it was equal to 0, then I should take the S out of it. Does that make sense? Anybody with me? Anybody confused? The only way I can have P of S or Q of S equal to 0 when S equal to 0 if I have S multiplies a polynomial, isn't it? The only way this P of S is going to equal to 0 if there's an S or S to a factor that multiplies the polynomial. But I took that S out. So therefore, what is left here is P of S does not have any S in it. All good? Or should we clarify it more? We're good? Good. Okay. I'm afraid I'll clarify it more, make it more confusing. But keep in mind, we took any S in here, in P of S, any S in the original polynomial out. We canceled them, and we ended up with S to the n. The only way this will equal to any polynomial equal to 0 if it has an S in it, a free S in it. But we took these free S's out, so it could not have it in it. Okay, so if I take the limit as S goes to 0, what is this going to equal to? P of 0 is going to equal to a constant. Q of 0 is going to equal to a constant. A constant over 0, what is it going to be? Infinity. I feel students are hesitant to say infinity. It's like they don't use it unless like they're pushed to the limit. It's going to be equal to infinity. And therefore, the steady state error is going to equal to 1 over the 1 plus the limit as S goes to 0 of G of S, which is going to equal to 1 over 1 plus infinity, which is going to equal to a 0. So therefore, we can say that if the system type is 1 or higher, then the steady state error due to a step is going to equal to a 0. Together? Okay. So therefore, if I have a step input and I'm trying to calculate the steady state error, if it is system type 0, then the steady state error is going to equal to 1 over 1 plus Kp. If the system is type 1 or higher, the steady state error is equal to a 0. And what does that physically mean? If I'm applying a step and there is an error, but the system has an integrator in it, what is the system going to do? It's going to integrate it such that it's going to force the system to react to that, the output of that integration, so that it's going to force the steady state error to go back to 0. Make sense? Which is, I mean, something it's easy to visualize and understand. If we're applying a step at the input, then at the error signal, we're going to have a tiny error, but then the system has an integrator in it. So this is going to get larger, forcing the system response to force the steady state error back to a 0. And this is mathematically what we're getting, if it is type 1 or higher. So all what we need is one integrator in the system to have a steady state error that is equal to a 0. And that is because the step is a very slow function. isn't it? Just a constant. Very, very slow. Okay, let's see what happens next if we're applying a ramp input. So we have a ramp R of t equal to t u of t. R of s is equal to 1 over s squared. So from this expression, the start one, from star, the steady state error is going to equal the limit as s goes to 0 of s multiplied by 1 over s squared multiplied by 1 over 1 plus g of s. S from the final derivative, 1 over s squared is the input. And therefore, this is going to equal the limit as s goes to 0. S with s is going to cancel. We're going to end up with s plus s multiplied by g of s. Okay. We're going to define kV as the limit as s goes to 0 of s multiplied by g of s. And therefore, continuing on the side there again, what is this limit going to equal to? When s goes to 0, s is just a 0. So this is going to equal to 1 over the limit as s goes to 0 of s multiplied by g of s, which is going to equal to 1 over kV. And we're going to call this the velocity error constant. Okay, so we're going to do something similar. What happens when we have different types of systems? So we're going to have 3 types of responses of outputs. Okay. So first, when we have a type 0 system, we're going to see what happens when we have type 1 and what happens when we have type 2 or higher. Okay. So if we have a type 0 system, what is g of 0 going to be equal to? Constant. It's going to just equal to a finite constant. Again, type 0, there's no integrators in the denominator, so it's just going to be, when we evaluated it at 0, it's going to just equal to a finite value. So therefore, the steady state error is going to equal to 1 over the limit as s goes to 0 of g of s and what? Oh, multiplied by s. What is this going to equal to? Infinity. Together? Again, this is from what we have here. 1 over the limit as s goes to 0 of s multiplied by g of s. If it is type 0, g of s is finite. Then I have 0 multiplied by a finite value, and that is going to give me infinity. So therefore, we conclude here that if I have a type 0 system, this type 0 can't track a ramp input. And what that means, if I have a ramp at the input, this is my input, what is my output going to look like? Something like this. This is output. This is my input. And if I calculate the error, this error is going to go to infinity when t goes to infinity. This is going to keep growing bigger and bigger. Okay. So let's look at what happens if we have a type 1 system. Steady state error going to equal to 1 over the limit of, as s goes to 0, of s multiplied by g of s. This is going to equal the limit as s goes to 0 of s multiplied by p of s divided by s multiplied by q of s. Because it's a type 1, I can write it as s to the 1 multiplied by q of s. And therefore, this is going to equal to, I can cancel the s with the s, and this is going to equal to q of 0 divided by p of 0. And therefore, this is going to equal to a finite value. And this is going to equal to 1 over kV. Together? So what does that mean? If I have a ramp and I have a system that is type 1, then the output might look something like this. It has an error, but this error is finite. Okay. Let's see what happens when you have type 2 or higher. Same thing, the steady state error, 1 over the limit as s goes to 0, sg of s, which is going to equal to 1 over the limit s goes to 0 of s multiplied by p of s divided by s squared or higher multiplied by q of s. S with s is going to cancel. We're going to still have s in the denominator of the denominator. So therefore, we're going to have 1 over infinity, which is going to equal to a 0. And therefore, if I have a system that is type 2 or higher, if I have a ramp, then in the steady state, the error is going to equal to a 0. Is that clear, everybody? Okay. We'll stop here, and next class we'll continue with if we have a parabolic input, and then we'll look at what happens if we have a non-unity feedback. Okay, since we have a minute, let's take attendance.